Welcome to theme 2.2, where we will be discussing how to write double integrals in polar coordinates. So sometimes it is easier to just write a certain region in terms of polar coordinates than Cartesian coordinates, like we did it in 2.1. So there are some very important equations that we use for polar coordinate transformation. And these we will be using. So if you want to pause the screen to just write them down somewhere, you can do that. So first we will do an example to illustrate the difference between the Cartesian coordinates and the polar coordinates. So let's say you had a region that looked like this. So you had a quarter circle where the circle is x squared plus y squared is equal to 4. And you wanted to integrate it to get area. Or in this case, we have a height function, so you just integrate it to get volume. So normally, what we would have done is we would have chosen either type 1 or type 2, and then we would have looked, let's say we chose type 1, we would have said y goes from 0 to 2, and x goes from 0 to this function. So this function, we would have had to write x on its own in terms of y. So in the Cartesian coordinates, the integral would look like this. And for the polar coordinates, we turn the x and y into r, and we describe a theta. So theta is basically the angle between a line and the positive x-axis. So in this case, we change our height function. So previously our height function was x squared plus y squared, but we know that x squared plus y squared is equal to r squared. And now we have to find our boundaries for this. So we can see that this would go from 0, pi over 2, pi, and 3 pi over 2, and then 2 pi. Your r, which is your radius, is how far your line or your function is from the origin. It basically just describes the region in which your r is, the distance from the origin. So in this case, your r is between 0 and 2. And your theta is in between 0 and pi over 2, because it only goes from 0 to pi over 2. And then you can write your integral like this. You have it going from 0 to pi over 2 and 0 to 2. Your height function is r squared. Now something very important to remember is your integrating factor. So when you go to polar coordinates, you always have this integrating factor of r, which you have to include into your integral. So then you multiply it into the r squared. Okay, so example 2. So in example 2, D is the region inside the circle x squared plus y squared is equal to 8x, but outside the circle x squared plus y squared is equal to 4 squared. Give an iterated integral in polar coordinates that may be used to find the area of D. So first thing we always do is we draw what our regions look like. So in this case, our regions look like this. We have two circles, one which has been moved to the right and another which is on the center. So the region we are looking at is outside of the blue circle and inside of the orange one. So this is just how we got the equation for the outside circle. I hope you can remember how to complete the square because we will be using it a lot. So then we find our boundaries. So we know that our r squared starts here and it ends here. So it doesn't start at 0 because that's not the area. The area starts here and it ends here. So we have to find a way to use this line and that line to describe our r. So x squared plus y squared is equal to 16 can be written as r squared is equal to 16. So r is 4. So r starts at 4. And x squared plus y squared is equal to 8x can be written as r squared is 8r cos theta. And then we know that r ends at 8 cos theta. So r is in between 4 and 8 cos theta. And then if we want to see what theta is, we have to know where these two circles collide. So we need to know what's this point and what's this point, because we need to know where theta starts or where it ends. So in this case, you can equate the two circles, and then you will find that they intercept at y is equal to plus minus root 12. So then we say tan theta is equal to minus root 12 over 2. That's for the intercept at the minus y. The 2 we got from saying 8x is equal to 4 squared, so we equated the two equations, and we got that x is equal to 2. So the intercept is at minus root 12 and 2. So then we just say tan theta is equal to a y over x. So our first angle is minus pi over 3. So this is where the theta starts. And then our second angle will just be pi over 3, because instead of having minus root 3, we will have root 3. So our theta is from negative pi over 3 to pi over 3. Therefore, our integral will look as follows. We will have theta interval on the outside, and we have our r interval on the inside. And remember the integrating factor that we have to add in. And then when you evaluate it, you just integrate. So we first integrate towards r and then towards theta. Then once you've done all of that, you'll find your answer being minus 16 pi over 3. So just check your integration along the way to make sure you are doing it right. So example 3, we say evaluate the volume of the region bounded by the paraboloid and the plane z is equal to 3. So first thing we do is we draw what it looks like. In this case, it looks three-dimensionally like this. This is your paraboloid, and this is your plane z is equal to 3. So it cuts it here in a circle. So we want the region here at the top. So it's in between z is equal to 3 and the paraboloid. So we have our height function. We say the paraboloid minus 3, because the height will be from the top, which is the paraboloid, and 3. So this would be our resulting height function. And then we can see what this area looks like on the xy plane. How we do that is we can equate these two functions to see what the resulting function would look like on the xy plane. So it looks like this. So here we equated the two functions, and that led us to a circle which is x squared plus y squared is equal to 3. So on the yx plane, the cut of the z is equal to 3 to the paraboloid would look like this. So we can get either Cartesian or polar coordinates for this integral. Since we're working with polar coordinates, we are going to do polar coordinates. So we need boundaries of r and theta. So since this is a circle, r is going to go from 0 to root 3. And we can see it's a full circle, so theta goes from 0 to 2 pi. And that would give us So this would be our resulting integral, where you just, instead of having 3 minus x squared plus y squared, you'll have 3 minus r squared, remembering your integration factor, and then dr d theta.